All right, so on the website you had last night, you actually had a little bit dealing with the families already on. So hopefully that wasn't too much of a concern to you or too overwhelming. But if we quickly kind of rattle through here, the metals, which is what the first slide is. Again, the first column in the periodic table, excluding hydrogen. Hydrogen's a non-metal, put in the first column because it's one valence electron. Those are the alkali metals. And the most reactive metals by far. And I know in Chem 1 I would do a demonstration where I put sodium metal in water and start a little fire on top of the water. They're not what you consider really metallic in that they're soft. But in general, metals are good conductors. When you think of metals, they're in wiring for electricity. They're good conductors of heat as well. We'll talk a little bit more about metallic bonding later in this, either this unit or the beginning of next unit. I forget which of the two it is because I'm kind of working on both right now. Alkaline earth metals are your second column. Again, as the trends go, so do the families go, where the second column is not as reactive as the first. Then your transition metals are the ones in the middle of the periodic table. Again, your D. We don't deal with the F orbital much at all in this class because, again, a lot of that down there is starting to get into your nuclear decaying type things. Fairly less reactive. Again, I say it varies in the number of valence electrons because, as you have seen when we did electron configuration last class, it gets a little goofy in the middle of the periodic table because it's not as easy to achieve stability as it is for other things. So again, hopefully you've got those first few blanks filled in on that note sheet. So I can rattle off the second and the last slide for the family part of it. Metalloids are those elements on the staircase. Now, if you don't recall, there's a staircase that separates out the metals from the non-metals on the periodic table. Again, hydrogen being excluded. But your metalloids typically start with silicon, germanium, arsenic, antimony, tellurium, polonium, although polonium radioactive, so it's another element we kind of ignore. So everything to the left are metals, everything to the right is non-metals. However, when you're directly on that border, you have a little bit of properties of both. Silicon is decent at conducting. I mean, there's silicone chips and pretty much everything that we have now that's useful. And that's on the non-metal side, yet it's a metalloid. I like to use the analogy, if you live on the U.S.-Mexico border, there's a good chance you know a little bit of both languages because you are right there, you have a blending of both. The further away you get on either end of that, the less likely you have to be able to know a little bit of both languages because you're further away from that. Halogens are the second to last column on the periodic table. Again, fluorine on down, the most reactive non-metals. I mentioned all three states of matter because remember, our periodic table up on the wall is color-coded, where elements that are red are gases at kind of normal-ish conditions. Blue is a liquid, black is a solid. The reason why they're all three different states of matter is dealing with intermolecular forces, which we cover in the next unit. So again, there's going to be a lot of connections as we get further throughout the year. Writing your first quiz in this class is very much more direct than later unit tests or a semester exam could be, because the AP exam will take a little bit from this topic that you did in November, a little bit from this topic in September, and a little bit of this one for February. And they'll put it somehow all in the same question with a part A, part B, part C. So when I mention things like this, that's more leading into the future. Finally, noble gases. Again, they are not reactive for the most part. I say that because if you look closely at the periodic table, there are oxidation numbers for krypton, xenon, and radon, meaning that it can be in a chemical compound, which is unusual, but if those gases are pressurized, typically with fluorine around, it's so reactive, it will be forced to bond and make compounds. Now, those compounds disobey the octet rule, a rule that you held dear in Chem 1 that isn't actually always the case. However, we usually will not worry too much about those being reactive. But if you ever saw something like a xenon tetrafluoride, don't be thrown off that xenon is bonded to something. It can't happen. Again, that stable octet is kind of that rule of bonding, and we went over that a little bit last class in terms of electron configuration as well, especially with those transition metals and how they're a little goofy. So, my goal here is to remind you of the stuff we went over in Chem 1. And then from there to tack on a little bit too. Atomic radius was the first trend that we went over in Chem 1. Because in my mind, if you can understand how the size of the atom changes left to right, top to bottom, you can understand the other trends. Remember that term last class, Coulombic attraction, that idea that a positive nucleus can attract to negative electrons, or absolutely charged anything can attract to anything else. If atomic radius is the distance from the nucleus to the outer electrons, and again, it's a really tiny distance, that's why it's measured in picometers. As you go down the periodic table, you gain another shell of electrons. Think of the Bohr model, that each energy level has its own ring, if you will. So it makes sense that the radius is getting larger as you go further down. The one that sometimes throws people off is as you go across a period, the radius actually gets smaller. And that's because as you go left to right across a period, you have the same number of shells. For example, sodium has 3 shells, it ends in 3s1. Chlorine has 3 shells, it ends in 3s2, 3p5. So they both have the 3 shells. However, chlorine has more protons, 17 protons, than sodium's 11. So now it has more positive in its center to attract those negative electrons and pull them in a little bit closer. So that's the trend that throws people off. But if you think about that then, that chlorine is smaller, that leads us into the fact that chlorine now is better at gaining electrons because its positive nucleus can attract other things. Sodium is bigger, it can't hold on to its electron very well, it's easier for it to lose electrons. So I know in Chem 1 we focus on atomic radius first because big things, easier for them to lose. Smaller things, easier for them to gain. Now one thing we didn't focus on as much in Chem 1, and it was one of those things listed for our goal sheet today, was ionic radius. So in other words, after you've gained or lost an electron, are you bigger or smaller? I'm hoping that you are fine with the term anion, negative ion. An anion is larger than the atom it came from. So let's use the chlorine example. Chlorine, if it's a -1 charge, halogens gain 1 electron to be like the octet. Chlorine -1, so chloride ion, is slightly bigger than the chlorine atom. On the very bottom, there's 2 determining factors for the size of the atom. And this one really goes into electron cloud repulsion. What I mean by that is both Cl and Cl- have 3 shells of electrons. However, Cl- has 1 more electron in that shell. And now you have 8 electrons in that 3rd energy level. Electrons are all negatively charged. They all repel each other. So if you have more negatives in that same shell, they repel, they get a little bit further away. That kind of bumps it out a little bit, makes it a little bit bigger. Some people like to think about the fact that, hey, the number of protons is the same in the center. It's harder for 17 protons to pull in 18 electrons than 17. That's a reasonable way to think about it too. Usually, College Board prefers you to talk about that idea of repulsion, but I think both ways are justifiable. Cation is a little bit easier, especially if it's an alkali metal or an alkaline earth metal. If sodium loses 1 electron, not only does it lose an electron, it loses the 3rd shell, because now it's isoelectronic with neon. 3 shells versus 2, that's pretty easy. A little bit harder to think about is what if cobalt or iron or one of these other ones lose an electron here or there? Because it's not as much of a given that it's going to lose an entire shell based upon how many it loses. However, typically you lose the outermost. So even when we say iron plus 2, you should be losing the 4s2 electrons first. But once you lose electrons, another way to think about it is that there's less electrons in that same shell to repel each other. So now if they don't have to repel each other, they're more attracted to the nucleus, they squeeze in a little bit. So again, cations, typically they're losing an entire shell. That's what makes them smaller. Even if it's just calcium losing 1 electron though, so not getting to the octet yet, but losing 1 electron, there's less repulsion in that 4th shell. It can be in a little bit. Typically, I would see this with multiple choice. However, I could see someone asking you to, say for an ion, write the electron configuration for it, and then explain why it is bigger, smaller than its neutral counterpart. All right, so ionization energy, something that we went over in Chem 1. And again, if you recall the photoelectron spectrographs from last time, they referred to it as electron binding energy. It is actually a measurement because with the PES, you fire energy into an atom, you can measure how much energy you put in and then see, is that enough energy to make it lose that electron or not. So energy to lose an electron. Now here is where Chem 1 simplified, and I want to make sure, and the reading guide that we do at the end of the hour with ionization energy should cover this as well. In Chem 1, we taught you the trend left to right, top to bottom. The difference here is you could lose the first electron, so there's a first ionization energy. But then you could lose a second electron, a second ionization energy. You could lose a third, fourth. There's an ionization energy value for every single electron lost for these elements. Actually, last year, we did a new kind of computer lab with the trends that, again, seniors we didn't do because we just made it up last year. That kind of showed this a little bit. The key here I have is the second to last point. There's more energy needed to lose a second electron than a first. Just like there's more energy to lose a third than the second. Every time you lose another electron, it requires more energy to pull it away. We can think about the fact that cations are smaller, so now the electrons are closer to that nucleus, which means they have to overcome a greater amount of attraction to be ejected. But my focus on this slide is more about what we didn't cover in Chem 1. Because I'll talk about the left to right, top to bottom in a little bit, because I even mentioned that it's the same trend, left to right, top to bottom, as electronegativity. So I'll go over that when we get to the electronegativity slide. I wanted to focus more on, we never really talked about first versus second in Chem 1. We just said ionization energy. But there are different values for this, and it is something that you want to be aware of. However, again, very bottom slide here. Again, there's no desire or want within elements, and I had to make this clear on some of your labs when I graded them yesterday. However, we want to use personification for a second. Having a low ionization energy means it's easy to lose electrons. And if atoms are more stable with a octet losing electrons for metals, a lower ionization energy would be the preferred state for metals. Francium in the bottom left-hand corner is the most reactive element for metals on the periodic table. Now, granted, it's radioactive, so it's hard for us to really isolate it ever. But it's really big all the way down, which means its electrons are further away from its nucleus, so it can't really hold on to that well. It just loses it right away. So now, if we remind you of electronegativity, electronegativity is the exact opposite, where it's gaining or pulling on electrons. Now, the trend for electronegativity, as we look at the periodic table, which once again is the same as the trend for ionization energy. As you go left to right, electronegativity increases. Because remember, as you go left to right across the periodic table, the atoms get smaller. And if they get smaller, there's a greater chance their positive nucleus can attract a negative electron from a neighboring atom. And electronegativity is kind of the big trend that's used in this class and in chemistry in general. Because then we could talk about polar bonds and nonpolar bonds and things like that as well. If you recall that from Chem 1, we'll be going over that next week. So, even though ionization energy is important, ionization energy is about losing electrons, so that's an ionic compound then, metal losing to a nonmetal. Electronegativity can be used for both ionic, because that nonmetal has to be able to gain. Again, if you didn't figure it out or hear from others, why did the magnesium lose electrons to the oxygen instead of the nitrogen? Oxygen is more electronegative. So it's better at attracting magnesium who lost electrons. That's from the lab report that you turned in. As you go down the periodic table, electronegativity decreases. Atoms get bigger, which means their nucleus, that's the thing that's attracting a neighbor's electrons, is further away. Less coulombic attraction. Nonmetals with the high value are going to be the most reactive. Fluorine is the highest. And noble gases more or less don't have electronegativity values. Krypton does a little bit, xenon does, radon does, because again, those are a little unusual. But fluorine in the upper right-hand corner, the highest electronegativity. Heck, some of you in your lab report even gave me the electronegativity values for oxygen and nitrogen. Really, if you know those bookmarks of francium and fluorine, the further away you get from francium as a metal, the less reactive you are. The further away you get from fluorine as a nonmetal, the less reactive you are. The only weird thing, again, is hydrogen. Hydrogen is a nonmetal, so it is trying to gain electrons to reach noble gas configuration, not lose electrons. We will use H plus as a symbol for acids second semester, but H plus would just be a proton by itself. Hydrogen with one proton and one electron lost that electron. A single proton all on its own, that's not stable. What was it Emily was asking yesterday, what happens to these electrons that are lost in the PES? Again, you just don't have a random electrons floating around. Something attracts them and pulls them in. Same thing if it was ever an H plus. You just don't have a random proton laying around. So some students get confused about, hey, I see a +1 above that hydrogen. It means hydrogen loses an electron. If we were doing a periodic table based upon the trends, hydrogen would probably be right above carbon. So it's similar in electronegativity to carbon. That would probably be where we place it if that were the case. It's just that we don't do that because then that confuse everything else. All right. This brings us to electron affinity, our last slide of the day. Electron affinity is kind of a blending between ionization energy and electronegativity. But I'd lean more towards the electronegativity part because it is associated with gaining electrons. However, it is an energy value. So it is like ionization energy where it's a measured value in kilojoules per mole. So how good is fluorine at taking an electron away? Electronegativity isn't just about taking electrons, it's about sharing as well. That's why polar versus nonpolar plays a role in that. Electron affinity is dealing more with ability just to take an electron away. Again, I haven't seen this really brought up often. However, these values are given to you as a negative value because when an atom, particularly a nonmetal, gains an electron, it becomes more stable. It's getting closer to being the stable octet. And within all of chemistry, when you go from unstable to stable, energy is released. Like we talked about that in nuclear chemistry. Why is radioactivity given off when alpha decay occurs? Well, it's becoming more stable. It releases energy. Again, when products are more stable than reactants in a combustion reaction, when we used to do activation energy curves in Chem 1. Again, we'll remind you of all that when the time comes. But this is kind of a statement true within chemistry in general, that when you are giving off energy, that means the system no longer needs as much energy to keep it all together. It can give it off. And then my very last point numerically, you will find that, again, the bigger the values, the more energies that is released. My focus would typically be on electronegativity because it has more applications to other things we cover throughout this class. Ionization energy, though, ties in nicely with the photoelectron spectrographs, which we went over last time. So in my mind, electron affinity is a far distance third. And what surprises me is when I looked at that goal sheet, it even popped up. Because 2 years ago, they said you didn't even need to know electron affinity. But now with this redo that they're doing, they decided to put that back in there. I wanted to make sure to at least address it a little bit. It's a measurement of how well an atom can take away an electron. Electronegativity does have numerical values associated with it. Those are man-made numbers. I don't know why they decided to give fluorine electronegativity of 3.98 or 4.0 if you did 2 sig digs. But someone decided to do that, and then they just made numbers based off of that, of how far is oxygen from that, how far is chlorine from that, so on and so forth. The only advantage to electron affinity is these are actual measured values, the energy to take an electron away.